Okay, we are going to look at the logistic model of population growth. And in this particular lesson, I will look at it from the perspective of differential equations and the AP Calculus BC curriculum. There are other applications of the logistic model, but I will not get into those. This is going to be catered more towards what you see in AP Calculus. And if you need to print a hard copy of the problems I'm about to talk about, you can go to bit.ly/logisticDE. So let's get going. The logistic model is typically used for population sizes. It doesn't have to be, but that's the textbook type application of it. And the logistic model is a more realistic model for population than the uninhibited exponential growth model, and that the exponential growth being AE to the KT. And the reason the logistic model is more realistic is because it factors in something called carrying capacity. And depending on what science you have taken in the past, you may or may not know carrying capacity is the maximum number of organisms an environment can support. So things that can impact how much the environment can support would be disease, how much food is available, how much space do you have, how much water is there, are there natural predators, is mate selection ideal? All these things can factor in your carrying capacity. Exponential growth doesn't factor in any of that. Exponential growth kind of works under the assumption that you have an infinite amount of space and resources and there's no enemies and this is perfect utopia. And it's not very realistic on the long run. Sometimes for short periods of time, exponential growth can be accurate, but it doesn't hold true for a long period of time. And that's where a logistic model has a bit of an advantage. So a few things about the logistic differential equation. This is what the logistic differential equation will look like. It can be presented in other ways. I should say that this is my preferred form of your logistic model. dP/dt is Kp times 1 minus P over C. P would be the population of your rabbits or whatever it is you're talking about. T is your unit of time. And obviously the unit can change depending on the problem. K is some constant that is related to the growth rate. C is also a constant, but C is specifically the carrying capacity of your population. Do note that your logistic model can be presented in other formats, and I personally prefer to take any other representation of the logistic model and turn it into this format. I strongly believe this one up here is the one that is easiest to read and decipher. So if I see something in a format kind of like this first one down here, P prime of T is 0.15P and all that other mess, I would start by realizing that I don't have 1 minus P over C, and if I want a 1 in the place of this, I will need to factor out that 0.15P. When I do that, I'm left with 1 minus something. I do know that P times another P will give me P squared. And if you happen to divide a 0.15 out of a 0.00075, you get 0.005, which is the same as 1 over 200. And so now I have this logistic model in my preferred format, and I can look at this and very quickly tell that my carrying capacity is going to be 200, which is good to know. There are a lot of questions that if you know the carrying capacity, you can answer the questions almost immediately. The second example here is very close to my preferred format, but you'll notice instead of a 1, there is a 3, so I will need to factor out that 3. And if I factor a 3 out of this, I'll be left with 1 minus P divided by 300. Now there is still a 0.01P, or 0.1P, 0.1P right here. So 0.1 times 3, that would end up giving me 0.3P times 1 minus P over 300. And again, I like that format because I can look at this and very quickly tell carrying capacity is going to be 300. And so there's the logistic differential equation. But let's talk about the solution to the differential equation, because differential equations do have solutions that come with them. And this is what your solution to the logistic model would look like right here. And if you took, or if you addressed logistic models in pre-calculus, you were probably just given this format right here. And then you had to use that to answer certain questions. The C in the solution is the same C that is in the differential equation, and the K that is in the solution is the same K that is in the differential equation. The only thing that you would have to find yourself is this constant A, and unfortunately, A is not your initial population like it sometimes is in your AE to the KT format, if you call it A in that application. So to get A, if you want, if you want the initial population, you actually need to plug in 0 for T. So if I do want my initial population, you'll plug in 0 for T. And in the generic solution, that ends up giving 1 plus A e to the K times 0, and e to the 0 is 1. So it turns out your initial population would be found by figuring out what C divided by 1 plus A is. You could memorize that. I do know some teachers will say, hey, let's memorize that. But it's so easy to just plug in 0 for T. I don't bother using any brain space memorizing that. I'll just plug in T equals 0 to figure it out. So let's look at some questions. And we're going to start with a slope field representation of a logistic model. And this is one that I just kind of made up on my own. We have a population of gnomes given that follows this differential equation. That is the logistic model. Usually, not always, but usually they will tell you it's the logistic model. I don't think they should do that. I think you should look at it and decipher that yourself, but they often will just tell you it's logistic. You are provided the slope field for this particular model, and P of T is a solution to this that satisfies the initial condition P of 0 is 20, and you are asked to sketch the solution curve to represent P of T, and that means we are starting with an initial population of 20. You may have a hard time reading these numbers, but along the y-axis right here, along my vertical axis, I have little marks at 20. Here's 40, 60, 80. Here's 100. That's 120. So there's the carrying capacity. It's not coincidence that we have a row of 0 slips right there. And I'm starting with a solution that starts at 0, 20. And I notice that I am increasing. I have a positive slope, and we are slightly concave up at the beginning. So I'm going to start by going up with a concave up, and this may take me a minute to do fairly well. We're increasing, we're concave up, and then at some point, we flip to concave down. So I'm going to flip to concave down following these slopes, and eventually we approach that horizontal section up there. And that will be a pretty good solution. I'm pretty proud of that. I'm surprised I didn't have to erase it and start over. And you'll see that we do trend upwards and we level off at 100, which, going back to what that 100 is, that is the carrying capacity. And so it makes sense that our carrying capacity is a horizontal asymptote. It's a kind of a goal for your population. You're going to trend towards that population carrying capacity, which is actually, I'm going to jump down here to number 2. It says limit as t goes to infinity. If time goes on forever and you are in a logistic model population, your population will always trend towards the carrying capacity, regardless of the initial condition, regardless of your initial amount. And so in this case, we will always approach 100. Even if I decided to fly over this island and drop 200 gnomes from a helicopter, if I drop 200 gnomes on this island, I'm way above carrying capacity, and you will notice that the slopes up here say that I'm going to start up here and we will trend down. They will start dying off because the environment cannot support them, and they will eventually approach that carrying capacity. So it doesn't matter where you start, as long as you have at least one organism, you will trend towards carrying capacity according to the model for the logistic growth. Now, the growth rate being the highest, this is an interesting question. When does the population grow the fastest? And the growth rate is the highest when our population is growing the fastest. That's going to be when we have the highest slope. And if you look at this, the highest slope appears to be, so we're concave up, and then we flip to concave down. It appears to be somewhere around in here. And the highest growth rate, I had to re-record this video because I misspoke originally. I originally said the highest growth rate is always half the carrying capacity. But there is one little caveat to that. The growth rate is the fastest if your initial amount is less than half the carrying capacity. So if you start with less than half the carrying capacity, then the fastest growth rate will be half the carrying capacity. And that actually happened in this model. We started at 20, carrying capacity was 50, that's right in the middle. Carrying capacity was 100, half of that is right here. And we started below that. So we trended concave up, then we flipped concave down, and that inflection point is when growth rate will be the fastest. But What if I started with 80? What if I started right here? Well, I've already started my decrease in population growth. And so in that case, the fastest growth rate would actually be at 80 because we've already started slowing down. Now, that said, I've never seen this question asked where our initial condition was not less than half the carrying capacity. So just something to consider. But as long as you're starting below that halfway point, population will grow the fastest at the half carrying capacity. And that is a fact that is okay to memorize. You don't have to justify that or explain that in great detail. So let's move on and look at another couple more questions. This is from the 2004 BC exam, number 5. We have this particular logistic model. And again, they tell you it's logistic. They don't tell you what the population is. Wherever it is, they live in a very small place because carrying capacity is only 12. Only 12 can be supported. And the first two questions are immediate. If my initial amount is 3 and if my initial amount is 20, what does the population approach as time goes on forever? And well, if time is going on forever, you will always, always, always approach that carrying capacity. If my initial amount is 3, that's below my carrying capacity. So we're going to increase until we get to that carrying capacity. And if my initial amount is 20, we have more than the environment can support. So we will decrease and we'll crash towards that carrying capacity. And I have a weird return in this. I don't know why there's a C right here. I'll just wipe that out. If my initial condition is 3, if I have 3 at the start, for what value of P is the population growing the fastest? And I notice that my initial amount is less than half the carrying capacity. Half the carrying capacity is 6. I'm starting below that. Therefore, population will grow the fastest when P is 6. So when P is 6, that is when population will grow fastest. And again, I'm not going to justify that. It is okay for you just to know that fact. And do pay attention. That is a value of P. That is the population, not the time that it happens. The time would be a much more difficult question to answer, but the population grows as fastest when the population is at half carrying capacity. And if you think about that from a logistical point, that means we still have a lot of room to grow. We have a lot of room for more organisms, but we also at the same time have a lot of organisms trying to create more. So it's a good mix of a lot of things trying to create babies and having room to grow them, and that would be at half carrying capacity. And then the last question I wanted to look at is from the 2008 BC multiple choice exam. This is number 24, and they give you a graph of a solution to a logistic model. And I can see that according to this one, my carrying capacity is 200, and we are trying to find a differential equation that matches that could possibly give this scenario. And all we know is carrying capacity. I can tell my initial amount appears to be, I don't know, it looks like 30 or 40, maybe 25. I don't know. I'm not 100% sure, but I do know carrying capacity is 200. So I'm going to go ahead and make a note that I think dP, I know dP can be written in the form something times P times 1 minus P over 200. That's what I'm looking for. I don't have enough information to actually solve for K, but I do know that it's going to be in this format. So I start looking at my options, and all of these have the KP distributed through the problem. So I'm going to see, well, if I distribute my KP, I'll end up with KP minus KP over 200, KP squared over 200. And so I'm looking back at my options, and here's the beauty of multiple choice. Only one of these are in the form of, only two of these are in the form of KP minus something P squared. And that is, it's either going to be A or B. Those are the only ones that are in the logistic model. Now I've got to figure out which of these two will give me a carrying capacity of 200, which means which one of these, when I factor out that initial number, 0.2p, that'll leave me with 1 minus something, p over something. And this one will also, I'm going to factor out 0.1p, which will leave me with 1 minus something. And we just have to figure out which of these is going to give me 200 in the denominator. And one thing that just dawned on me in 2008, multiple choice number 24, was a non-calculator question. So we have to figure this out without a calculator. And I honestly believe that's going to be easier if we think of this with fractions instead of decimals. So option A, I could rewrite that as 1/5 P minus, and that would be P squared over 1,000. And option B is 1/10 P times 1 minus, not 1 times 1 minus, 1/10 P minus, and that would also be P over 1,000. And if I factor out that initial amount, 1/5 P, I'll be 1 minus P over, and 5 times 200 does give me 1,000. So I really like option A now. Let's look at B just to be sure. I left out my P squared right there. That's 1/10 of P. If I factor that out, I'm left with 1 minus P over, and 10 times 100 gives me 1,000. I needed a carrying capacity of 200, so that confirms A was correct. And so there's my lesson on the logistic model, and I am sore-throated and ready to quit.